Hello everyone. In this video, I will present our work, Mask as Supervision, leveraging unified mask information for unsupervised 3D pose estimation. At the beginning, I will briefly introduce the background of unsupervised 3D pose estimation and our motivation. I would like to raise some questions to elicit the introduction. So, why unsupervised pose estimation? As we know, for ECCV vision systems, the 3D ground truth can only be accurately calculated or annotated in multi-view scenarios. While there are some multi-view databases in mocap environments, obtaining labeled 3D data remains a costly process. Furthermore, compared with in the wild 2D data, the quantity and diversity of 3D data are significantly inadequate. It ultimately hampers the performance of 3D human pose estimation. For the unsupervised HPE task, the method needs to bridge the gap from mocap to the wild. The next question is, why mask as supervision? Two conditions must be met for masks to be effective as supervision. The pose must be inferable from the mask, and there must be a method to extract this information. For humans, we can easily estimate key points from mask. It corresponds to rich priors embedded in mask, and we already acquire some human priors, including structure, shape, etc. Moreover, the mask is easier to acquire than pose annotation. Therefore, the remaining challenge is to enable machines to use masks effectively for supervision. Noticing the detector outputs point-wise results, and mask is in frame-wise format, we proposed a course-defined pipeline to eliminate the gap and refine the information. In detail, we propose a novel, unified framework utilizing mask as supervision. It incorporates skeleton and physique marks to discover body structure priors, and shape constraints to organize human skeletons, and improve pose estimation accuracy. Furthermore, geodesic weighting and a cascaded optimization scheme are employed to estimate challenging distant key points with smooth solution space. For skeleton mask, it focuses on the structure prior of humans. It establishes distinct interrelationships with articulated parts that collectively define the skeletal structure. Each valid bone connection in the human skeleton can be represented as an extended Gaussian distribution along the line segment defined by its to corresponding key points. With given connections, the physique meaning of each key point can be determined, and the gradient can be backpropagated from frame to point. As demonstrated in the experiments, the structure prior builds a connection from key points to shape maps, and effectively extracts skeletal information of the majority part within mask supervision. However, a gap still remains between the skeleton mask and the ground truth mask. The integration of a shape constraint could further narrow this divergence, culminating in a more precise 3D pose estimation. To address this, we propose the physique mask, and utilize a simple U-Net network ended with a sigmoid function that takes the skeleton mask as input and outputs a 0, 1 physique mask. The objective is a weighted combination of both skeleton and physique mask losses compared with the provided ground truth mask. Additionally, joints further from the root of the kinematic tree are more challenging to estimate due to the increased dynamics. To this end, we employ geodesic distance as a tool to augment the representation. The mask region is weighted differently based on its distance from the mask centroid, and the distance from the mask edge for the background region. Geodesic weighting is then integrated into the final loss function. Our approach achieves state-of-the-art performance on human 3, 6M and MPII NF3DHP datasets without relying on human annotations, which are commonly used in previous methods. Specifically, Supervised Post-Processing, SPP, which trains a network to map the predicted high-dimension landmarks to ground truth results and ignore the order of key points, will not be used from our pipeline since the structure prior is considered. There are quantitative results and ablation study to validate the effectiveness of our proposed components. As anticipated, using the skeleton mask allows us to model the human structure without the need for SPP. With the general purpose of unsupervised learning and bridging the gap between indoor and in the wild data, we explore the use of incremental data to enhance model robustness and generalization capabilities. By incorporating H36M, 3DHP, and in the wild TikTok data, our model shows a performance increase in the wild dataset MPII.